All right, today I would like to talk about another conservative interaction, because during the last lecture we discussed one source of potential energy. What was that? Gravity, correct. Gravity results in potential energy because gravity is a certain type of interaction. What do we call this type of interaction? Conservative interaction, correct. So for conservative interactions, we can introduce a concept of potential energy. And what's the purpose? Why do we introduce a concept of potential energy? Because it seems to me that there's one more quantity which we have and we calculate. But does it help? How does it help? Does it? Correct. It is easier to calculate work. We don't have to integrate force every time whenever we need to calculate work. Instead of doing that, we just have to find out what is the change in potential energy from one location to another location, and by subtracting initial potential energy from the final energy, we know that this is opposite to the work done due to this conservative interaction. All right. Another conservative interaction is elasticity. So now a spring, for example, will have such a property, and in a spring, the force exerted by the spring on its end, so whatever we attach to the spring, then the spring will exert a force on that, is proportional to the displacement from the relaxed shape of the spring. So let's say that when this point is at this location, then the spring is relaxed, and if we stretch or compress, it does not matter which way, for a spring, the spring will exert a force along its axis opposite to the displacement from that relaxed position, or from the equilibrium position. Over there, when this point is over here, the spring does not exert the force. All right. So let's now assign potential energy to, well, wherever that point is. And remember that potential energy is, we know potential energy for any type of interaction only with accuracy to a certain constant. That constant is determined by where we choose the reference for potential energy to which we assign zero value. Right? Like, for example, for gravitational potential energy near the surface, where do we choose potential energy zero? Well, like for me, my gravitational potential energy, where would you assign zero? Over here or on the other side of the room? Over here. And actually, why over here, not on the other side of the room? Think about how, yeah, because it is reasonable to assign potential energy zero to my current location, assuming that I'm going to walk around this room. Why it's better to choose it here than there? Because what? Because it's lower, so what? Yeah, this is the lowest point. I am in the lowest point. So how does this simply, because we choose potential energy in such a way that everything is simplest, that the calculations are simplest. Why when we choose the reference for potential energy over here, this will be the best place. Now, recall that we are on the second floor. In the building, if I walked around the building, what would be the best floor to choose the reference for my gravitational potential energy? The first floor. The first floor would be the best if I walk around the entire floor. Why? Because then the lowest, my lowest potential energy will never be less than zero. So what? Why? Why is it convenient? No. No, my starting point is here. Well, we will always have to deal with positive values. So we will not have to think, well, should I subtract or should I add? Well, potential energy would always be positive inside of the building. If we consider this room, if reference is on the top of this floor, then right now I would have negative potential energy. So we skip that minus, the negative sign from the numbers if I choose the reference for potential energy here. Now, how about the Earth or a planet? Why do we choose, where do we choose it? Where is the reference for potential energy? Yes? We picked it at infinity, far, far away from the planet. Why? Unfortunately, notice that in this situation, potential energy of every planet is negative. I mean, whenever object is in the gravitational field of a planet, potential energy is always negative. But why did we decide to do that? Because then the formula contains only one term. If we choose everywhere else, potential energy will have two terms. So just to get rid of this, because you remember that, yes, I mean, during the last lecture we found out that potential energy requires that we have inverse of distance from the center for the considered location minus inverse of the reference distance. Right? So that if we choose that reference distance to be infinity, then that term disappears. All right, let's come back now to the spring. And for the spring, it makes sense to choose the reference potential for a relaxed spring. So reference of potential energy will be when the when this point is at zero location where the spring is relaxed. Yes, hold on. I mean, so we have a question over here. Can you ask that question then?
I was just asking, what is the f of x? Is that a vector?
Oh, very good question. Yes, yeah, because now we will exercise again vector and scalar quantity. Is this f of x a vector or a number? Just looking at the notation. From that notation, according to you, it's a vector or a number, and tell me why. So people think that this is a number. Would you be willing to explain why did you figure out that this is a number? How it would be indicated otherwise that it's a vector? It will have an arrow, and actually we have kind of redundant notation because even on top of the arrow I use also a bold letter. The book would use bold letter. If you see a bold letter, then it will be a vector. And so let's now recognize what is that f of x. Say in English what f of x is to your neighbor. I see that some of you say that it's magnitude. Now, k is a positive number. Actually, it doesn't matter. If k was, there is a situation that this expression could be negative. Can you see that? Yeah, so let's say k is a positive number, really. It is called spring constant of a spring. And if displacement is such that x is positive, that expression has a negative value, which means that definitely f sub x is not magnitude, because if it were magnitude, it had to be a positive or non-negative number. Josh has an idea?
It's the force at which the spring goes back.
It's the force, but the force is a vector quantity. So if you say that it's the force, then it's wrong, because it's not a vector. Force is supposed to be a vector. X component, okay, X component is correct answer, although you are leaving still ambiguity. Which X component? Aha.
X component of the force vector.
Well, yes, of course, we are talking about X component of the force vector. Okay, so which X component of the force vector? No. No, displacement. X is displacement, and actually X is also a component of scalar component. Correct. This is the scalar component of the force vector. I buy that. All right. And it is in x direction. Yeah, because, well, if it were a vector over here, yeah, so if we were a bold letter and had f sub x, what that thing would mean, what that symbol would mean. It would be what?
The x component of the force vector.
It would be x component of force vector by which x component of force vector? Not the one which we identified over here, because right now we identified that this is the scalar component of the force vector. But the other one would be vector component of the force vector. I buy that. Correct. So over here, this is a number, and this is just a scalar component of the force vector. So the scalar component is opposite to the x scalar component of the displacement of that point, of the end of the spring. All right. So now if I want to assign potential energy at this location to whatever is attached to here, well, I would have to see by how much work is done from the reference point, because now potential energy at this point minus potential energy at the reference point to which I assign a 0 value. So here I have change in potential energy. Since I take it from the reference point, it happens the change in potential energy from this point to this point happens to be equal to potential energy at this point. Can you see that? It is only because potential energy at this point was 0. All right. So according to the definition of potential energy, it is supposed to be opposite to the work due to this interaction. What interaction we are talking about? Elastic, correct. You can even think about that this is kind of a tension force. All right, so I have to write down that this is opposite to the work done from that location to that location by the due to the interaction, so due to the conservative interaction. Now that work, so I copied that minus over here, and it is integral from the force. And x component of the force is minus kx, so I have x component of the force, x component of the displacement. Now the other two components of both are 0. So from the scalar product, recall how we multiply vectors when we know their scalar components. Which product are we using here, by the way? How many products do we know? 4. Correct. We know 4 products. Which one are we using here? Which one? The dot product, scalar product of 2 vectors. Now, we can calculate scalar product of 2 vectors easily 2 ways. If we know magnitude of the first vector and magnitude of the second vector, what else do we need to find out the scalar product? The angle between them, right? Because it is magnitude of the first vector times magnitude of the second vector times cosine of the angle. Now, if we know all scalar components of all vectors, what else do we need to find out the product? Faster? Mark? Nothing. We don't need anything. Yeah? We multiply first component plus first component, add the product of second component by second component, and add the product of third component by third component. Here, product of x components will give me, this is x component of the force, this is x component of the displacement. The remaining 4 components are 0. So I will have plus 0 times 0 plus 0 times 0. So I'm left only with this integral, and I do it from the equilibrium point, or from the relaxed position to the considered position. Well, I can take minus k in front because this is constant. Can I take x prime in front? What's the difference between x prime and x? What is that x prime? Not the derivative. These are the locations of that point as it moves from that reference location to the location where we calculate potential energy. So x prime will be, when this point is somewhere here, its x component of its position would be x prime. This one is a variable. This is really x also. However, it's a variable. This x says about the position of interest. Now, if you are skillful in integrations, you wouldn't even put that prime. You would recognize that this is variable and this is upper limit for the variable. So those two x's are different x's. All right. So I can take minus k in front, and let's use the fundamental theorem of calculus to find out the integral. So what is indefinite integral of x dx? X prime square over 2. Now I have to plug in the limits, and I get expression for that integral, kx square over 2. So spring constant times square of the displacement from the equilibrium location divided by 2 gives me what? Potential energy of the spring. Mark.
The notes actually.
Yeah, the notes. Oh, thank you. Thank you. So check if the notes say the same thing.
The note says negative kx squared over 2.
Then it's a mistake. Yeah. All right. How about if we plot now this function to imagine how potential energy varies? So the lowest potential energy which spring contains is when it is relaxed, and potential energy is 0 at that location. Why is it 0? Is it a coincidence? No, it was not a coincidence. How come that it's 0? We picked it to be 0, correct? We could say that it's 10 joules over here. What will be the difference in the plot? It would be shifted up 10 joules. Why don't we do that? Because it's easier to have 0 than 10. Correct. Yeah, so we pick up references in such a way that it's easiest, right? So now we have a quadratic function, and no matter if the spring is stretched or if spring is compressed, its potential energy increases as a quadratic function of the displacement from the equilibrium. Now, potential energy is, well, we have word energy. Kinetic energy has also word energy. So it makes sense kind of to combine them, although physics would exist if we do not combine them as well. Well, we do combine them and call it mechanical energy. So the sum of kinetic energy of a particle and potential energy of a particle is called mechanical energy. Now, it is that mechanical energy actually contains elements for which work can be easily calculated. And I advise you actually to remember by heart formulas for potential energy which we discuss. So potential energy of the gravitational field near the surface and far away from a planet, as well for the spring. And these will be the only three potential energies which we have to learn in this course. In the future, we will talk also about electrostatic potential energy, but this will be subject of the next semester of second part of the course. Now, kinetic energy is energy which is associated with the motion of a particle. Potential energy is related to position of the particle. So configuration. But now, do we know mechanical energy accurately or or not? Let's start with this. Do we know kinetic energy of a particle accurately or not? Only with accuracy to a certain constant. Kinetic energy of a particle. Only to a certain constant. So right now, for example, if I assign that now my kinetic energy is 10 joules, what would be my kinetic energy if I move with speed 1 meter per second? Does everybody agree that when I'm standing, my kinetic energy is 10 joules? Who thinks that I can say that my kinetic energy is 10 joules? Those of you who don't agree, you are right. Kinetic energy has a precise value. It is my mass times square of my speed divided by 2. So when speed is 0, kinetic energy is 0. However, now potential energy is associated with the position. When I'm in a particular position, do you know precisely my potential energy? No. It depends on the reference point. It depends where we choose the reference point. All right, so mechanical energy. Do we know mechanical energy accurately or not? No. We also know mechanical energy with accuracy to a constant. No, but really we are interested in changes in mechanical energies and changes in energies, because this is what is related to our effort described in terms of my effort is described in which affects energy of something depends on, I mean, what quantity do I use? A what? For energy, right. So if I do something, I put an effort to change energy of this object. How do I do that? By doing work, correct. So energy is related, I mean, the effort has to be expressed in terms of work. That directly says what happens to the energy. Now, energies, we introduce a lot of energies. We will learn about more energies in the future. And they are introduced in such a way that it cannot be created or destroyed. Energy can be transferred from one object to another object. Energy of an object can change a form. It can convert from one energy to another energy. So for example, if I think about a ball, if I toss a ball when it flies, because I mean, look, that at the top, kinetic energy drops to 0, right? When it is high, speed drops to 0 value. When it dropped to 0 value, it means that kinetic energy dropped to 0 value, right? Now, so what happened? In view of that, the energy could not be lost. Kinetic energy, object can lose kinetic energy. Object can lose potential energy. But if I add all energies for this object, I mean appropriately, I should recognize that it was not lost. So what happens with the kinetic energy of that ball? It is converted to potential energy. Potential energy is going to increase. When kinetic energy drops, potential energy is increasing. Now, on the way back, it appears that kinetic energy of the ball is increasing, right? Because at the top it stops, and then on the way back, it increases the speed, so kinetic energy increases, which means that something has to lose energy, some kind of energy. Well, actually, the ball is going to lose energy. What energy? It is losing gravitational potential energy. If a system is isolated, and actually when it is flying, when the ball is flying over there with relatively slow speed, I can assume that actually the system, Earth and the ball, is an isolated system. Nothing interacts with the system except we have an interaction between ball and Earth. That system, for that system, energy is conserved. So there are, if we consider systems which are isolated, then energy of that system total energy of the system, which means that I have to add various types of energies. However, I have to be careful not to count them twice, because if I add kinetic energy, potential energy, and mechanical energy, then it's wrong. I cannot change mechanical energy into kinetic energy. Why not? Because mechanical energy already includes kinetic energy and potential energy. So it is that I would count them twice. Do you see that? So be careful about that. And actually tomorrow I will try to cheat you. So be careful. I will be cheating you by confusing energies. Important thing is actually that you remember adjectives. So don't learn just energy. Always think what energy and of what. Yeah, I mean, precision is really important in this subject. So when we discuss force, we have always to think what exerts on what and how. When we talk about work, we have to answer 5 questions. Well, in in energy, we have 3 questions. Yeah, of what, due to what, and what type. All right. Now I want to show you second work energy theorem. Now, what I'm going to do tomorrow, I'm going to confuse the 2 work energy theorems. So be warned about it and try not to, study thoroughly both versions of work energy theorem, because so far we had, what was the first version? The first version said that change in kinetic energy of a particle is equal to the net work done on the particle. Meaning that net work, it is due to all interactions. So we have to add work of all objects interacting with the particle in order to determine change in kinetic energy. Now the second version of work energy theorem refers to this energy. What E stands for? Shout. Mechanical energy, which means that it includes both kinetic energy and potential energy. So if some of the interactions are conservative, we can actually combine them into mechanical energy, and then change in mechanical energy will be equal to the sum of change in kinetic energy and change in potential energy. I used here the definition of mechanical energy. Now, let's relate this to work. Change in kinetic energy is equal to which work? Which one? Not negative. Change in kinetic energy is actually equal to positive work, or due to, well, all work is always due to change in position, but due to which interactions? Change in kinetic energy is affected by, or kinetic energy is affected by what interactions? Conservative, for example, right? No. Gravitational? No. Work done by me? Yeah, well, so for example, think about this mouse, yeah? Its kinetic energy was affected now by what? Who changed its kinetic energy from value 0 to value 0? Who did that? I did? No. If I did that, that mouse would fly. Me and gravity is better, however, it was Earth. Correct. Why me and Earth? How about Amber? Amber, did you affect the kinetic energy? Did she? Why not? Because she was not interacting with the mouse. Correct. Well, it happened that here it was, I mean, I could include one more interaction. Air, correct. Air was interacting. So change in kinetic energy is due to all interactions of the object. All right, so over here is a change, it is work done due to all interactions. How about now what affects this one? Change in potential energy. Let's come back to the mouse. What affected potential energy? I did. I mean, is it related to my work? No, it's not related to my work. It is related, therefore, to gravitational work, because, I mean, we identified that there are only two significant interactions. If we included air, we could consider air. We would have to exclude it. Now, why? Because potential energy is associated with the work due to conservative interaction, correct, and gravitational interaction was conservative, therefore it affected potential energy. It is related to change in potential energy. All right, so I can write it down that this is equal to the net work minus work due to conservative interactions. Well, if from net work, which was done by all objects, I subtract work which was done due to conservative interaction, it means that I get work due to non-conservative interactions. Now, it can happen actually that you do not identify properly what are conservative interactions and non-conservative interactions. Therefore, I prefer to phrase that work-energy theorem in such a way that work NC is work done due to all interactions which you have not included in potential energy. So if some of the interactions on the particle are conservative, then the work done by all forces not included in the potential energy is equal to the change in mechanical energy of the particle. All right, so for example, I bet that you watch bungee jumping. Yeah, so now let's identify who is anybody performed the jump? Who jumped? Who did jump? I mean, from time to time there are people in my class who did jump. Well, anyway, who has an idea how it looks like? Okay, good. Now, let's find out which work actually affects the kinetic energy of or what energy does it have where? Yeah, so let's say that we choose, I mean, on the ramp that all potential energy on the ramp are 0. So what will be the kinetic energy on the ramp when the person starts the jump? 0, correct. Find interactions now. What interactions we will have to include for that person who jumps? What interacts? There is a gravity, correct? So Earth exerts a gravitational force. Should we include it in the gravitation as a conservative into potential energy or not? Who votes yes? Let's make it a vote. Who think that gravitational gravitational interaction should be included in the potential energy? We have 1, 2, 3, 4. Who thinks that we shouldn't? Well, okay. Nobody wanted to exclude it. Indeed, we can include gravity as a, well, we recognize that gravity is conservative interaction. Therefore, we can introduce a concept of potential energy, and we will therefore include it into mechanical energy of that person who jumps. Okay, let's go for another interaction. Elastic interaction, right? From where? From the what exerts the elastic this elastic force? What? The bungee cord, correct. Now, should we include this in potential energy or not? No. Who votes no? Who supports no? Who thinks that we should include it in a conservative interaction? We decided not to include it. Let me tell you that we could include it. Elastic interaction is conservative, so we could say that we could create potential energy with that, combine the two potential energies, gravitational and elastic, and have combined potential energy. You have decided not to do it. It's fine. Because now, change in mechanical energy, I mean, let's say a person jumps. And consider now the change, I mean the jump from the top to the lowest point. So at the highest point, gravitational potential energy was 0, kinetic energy was 0. At the lowest point, what will happen with the gravitational potential energy? No, we said 0 was on the platform. So here it will drop to negative value. All right, so gravitational potential energy would be 0, negative. How about kinetic energy? Will be 0 also, right? Because at the lowest point the person stops. So change in mechanical energy was, therefore, would be, yeah, so at the top mechanical energy was 0, correct. At the bottom, kinetic energy was still 0, but potential energy was negative. So mechanical energy was negative. Change in mechanical energy, therefore, was, did mechanical energy increase or decrease? No, it did. Yeah, because at the top, both were 0. So mechanical energy was 0. At the bottom, kinetic energy was 0, potential energy was negative, gravitational potential energy was negative, which means that the mechanical energy at the bottom is negative. It changed from 0 to negative. So the change is negative. The mechanical energy decreased. Can you see that? It decreased. All right, so we have that mechanical energy decreased, which means that something performed negative work, right? Because work done by all forces not included in potential energy. And what did we include in potential energy? Gravity. What we missed to include in potential energy? The interaction with the cord. Now the cord, think about, did the cord perform positive work or negative work? Well, think about it. Well, first, until actually the person dropped to the distance equal to the length of unstretched cord, how much work was the cord doing at that time? 0, correct. And then the cord started to stretch. Why positive? Work was positive. Why? Because the person was going downward and the force was exerted which way? Upward, right? So displacement was down, force was up, therefore work was positive, right? How did you get it? Magnitude of the first vector times magnitude of the second vector times cosine of the angle between them. And cosine of 180 degrees happens to be 1, therefore it's positive, right? Wrong. How much is cosine of 180 degrees? Negative. Yeah, remember, whenever force and displacement are in opposite direction, work is negative. Whenever actually the angle between the force and displacement is greater than 90 degrees, work is negative. When it is less than 90 degrees, it's positive. All right, so the bungee cord was performing negative work. Well, at least, does it make sense? Yeah? Why does it make sense? I mean, look at the work energy theorem. Do the things agree? Yes, because this one decreased, mechanical energy decreased, and this interaction, which we have not included in the potential energy, was negative, resulted in negative work. So this negative work is equal to negative change in mechanical energy. Now, let's say that we were so dumb that we didn't notice that gravitational interaction was conservative either. How would we look at that? What would be the... yeah, so now let's say that we missed that gravitational interaction is conservative and that spring produces conservative interaction. So what is the change in potential energy then? Consult with your neighbor. What is the change in potential energy if we do not have conservative interactions at all? Zero, correct. Potential energy is, we don't have potential energy, so mechanical energy would be only associated with the kinetic energy. All right, so now what would be change in mechanical energy in such a situation? If we consider it that way, if we solve the problem that way, it is an alternative solution of the same problem. Change in kinetic energy now is zero. Yes, so change in mechanical energy is also zero because it is associated only with the change in kinetic energy. We don't have potential energy at all. All right, so how come that the change in kinetic energy could be zero? Now, what will be the, change in mechanical energy is zero. What is the change in, what is the work done by the remaining forces? What forces would we have to include now? What interactions would we have to include to calculate work due to non-conservative interaction? All of them, which means there are just two. Gravitational interaction and the interaction with the cord. Let's figure out, well, we figured out that cord performs negative work, right? Think about work done by the Earth. Is it positive, negative, or zero? Positive. How do you see it? Josh, can you see it that it's positive this time? Mm-hmm. How?
The cosine between the two angles?
Because now the displacement is downward and the gravitational force is also downward. So the angle is zero. So it's magnitude of the force, magnitude of the displacement times cosine of the angle. That one will be even easy to calculate because gravitational force is constant, so it will be really force times the entire displacement. We couldn't do it for the cord. For the cord, we would have to integrate it if we miss that it is conservative interaction and use the quadratic formula for the elastic potential energy. Now, if we are really smart, we could find out that both are conservative interactions, how the problem would look like then. How much non-conservative work would be done? Zero. Why? Because nothing else is going to work. We will see it tomorrow, what would happen if nothing else were working. But at the current understanding, if we recognize that in the jump there is only cord and the Earth interacting, then the non-conservative work would be zero. All right, so this is going to be all for today. See you tomorrow.